crew module will then be put into its recovery cradle and ready for offloading. The ship will then begin the journey back to Naval Base San Diego. The team also is prepared to use an alternative method of recovery in case Orion can't be recovered using the ship's well deck. At sea, a sling will be placed around Orion, and the stationary crane on the USNS Salvor, a salvage ship, will be used to lift the crew module up and onto the deck, where it will be secured. It will remain there for its trip back to port. In case of very turbulent sea conditions, the USNS Salvor could tow Orion along until calmer seas are reached and it can be recovered. When Orion splashes down in the Pacific Ocean, the U.S. Navy ship and recovery team will be ready to recover the spacecraft and safely bring it home.
morning for a launch in Florida. Five, four, three, two, one, and liftoff at dawn. The dawn of Orion and a new era of American space exploration.
Well, hello everyone, and welcome to today's Orion post-flight test briefing. Orion launched from Florida this morning at 7:05 a.m. and splashed down in the Pacific Ocean about 4.5 hours later, about 600 miles southwest of San Diego. Crews right now are in the process of recovering Orion. Here to share more about how the flight test today went are William Gerstenmaier, Associate Administrator for Human Exploration and Operations, Mark Geyer, Orion Program Manager, Mike Hawes, Lockheed Martin Orion Program Manager, and astronaut Rex Walheim. We'll start with some opening remarks here, and then we'll have some time for questions. Bill?
Thanks, Rachel. Again, what a tremendous honor for me to be here to really thank all the folks that made today happen. You know, from the United Launch Alliance team that gave us the Delta IV, that gave us the ride to orbit. What a tremendous job they did in preparation and getting the vehicle ready to go fly and to doing their activities and making it look pretty easy. And then to the NASA team and the Orion team and the Lockheed team that just did a phenomenal job of getting Orion ready to go fly, and to see it execute this mission and work as flawlessly as these guys will talk to you about before. And again, I caution us all, we'll dig through the data. The first look looks really good from a data standpoint, but we'll dig through all the data and make sure that everything is there. We'll definitely learn some things from this flight. That's why it was a test flight. It will really help us as we take those next steps into the solar system with humans. And then thanks also to all the folks on site out at California. They're still busy, even as we're sitting here today, picking up the capsule. And the Navy teams and the helicopter teams and the other folks that are out there doing that activity and is just phenomenal. And even Space Station got to contribute a little bit. The Rapid Scat on board Space Station was able to provide real-time data in terms of the winds, the surface winds at the ocean during the pickup site. So even the station got to contribute to this activity. So what a tremendous team effort. And then I'd like to also thank just a little bit the folks that really got me excited again about spaceflight. I mean, to see the enthusiasm from the folks here at Kennedy and even for the media. I don't think I've been in a press event where you applauded coming in. You're usually sharpening your pencils and scowling at me with grimaces on your face. So again, thank you for catching that spirit that I think we all feel as human beings, that we as a species are meant to push human presence into the solar system, and this is a first step in starting to do that. So again, thank you for getting us excited again and thinking about what it's like to be really a leader in space. So thanks to everyone, and thanks to the team. Mark?
Well, let's see. It's good to see you after the successful mission. It's hard to have a better day than today. It was a lot of fun, very exciting, each part of the mission. Of course, part of the reason it's exciting is it's a difficult mission. It's a tough environment to fly through. It's tough objectives that we set for this flight. But it appears that Orion and the Delta IV Heavy were nearly flawless. Great job by the team. You know, even though I'm an engineer, I'm a fairly visual person, so these are a couple of things that I'll talk about, the things that I remember from the mission were the images. One of the big ones was the Delta IV Heavy, the beautiful liftoff we had at sunrise. Many of you were here yesterday as we talked about the difficulties with getting a great rocket like that started, you know, with the winds and other things that the team has to be very careful about to make sure we're ready to go and have a successful launch. They worked through those things yesterday, and today we got right off, right at the beginning of the window, flawlessly, terrific. And also the upper stage put us right where we needed to be. So I want to thank the ULA team, did a fantastic job. The other images that I remember were that we had a picture out the window. You might remember that one, and seeing the limb of the Earth at about 3,000 miles. What I liked about that view is, one, you can see the frame of the window, so you feel like you're an astronaut yourself. You're looking out the window. It's different than a satellite taking a picture of the Earth. It's what it would be like if you were inside the capsule on that mission yourself. So I thought that was very moving. And the distance we were from the Earth, which a human-rated system hasn't gone that far since 1972. And in fact, that mission was Apollo 17, which launched December 7th of 1972, so almost exactly 42 years ago. So that reminded us that, you know, here we are again now, the United States leading exploration out into the solar system. So that was a great moment. The other two visuals were the separation. We saw the heat shield as we separated, and also the entry, which was very dynamic. I want to thank the teams who got us those views, but you see how energetic the entry is and what the job the parachutes have to do, and it reminds you that this is a difficult job, and those systems have to work and have to work well and have to deal with very dynamic environments. So just hats off to the team. Just a terrific job. So the last thing I would say, and Mike will actually go through some of the specifics about how the vehicle did. You know, this Orion team, this NASA, Lockheed, and other key suppliers, as well as the ground ops team that's doing the recovery right as we speak, and the mission ops team at JSC, who helped us fly the vehicle, and the SLS team who made pieces on this article. They do incredible work every day. Today it's just more obvious to everyone else because we flew the flight and it performed so well. So I want to thank them, and it's an honor, a blessing to be a part of that great team. So I'll pass it to Mike.
Thanks, Mark. So I guess I'll just take from there with Mark. The team has done just an incredible job, and we had a chance to swing by and check in on the engineering teams who were still in the O&C before we left, and they're the folks on the Orion side that have been not just building the spacecraft, but powering the spacecraft and doing all of the engineering support for the test flight. You know, several years ago, when Lockheed won this contract, we had embedded in that contract the idea that we were going to build a spacecraft at the Kennedy Space Center, and that had not been done. And we have now done that. We have the team that accepted, you know, just that green pressure hull and added everything else that made that ship fly today. So it is a fantastic team with our suppliers across the country and our partners, as Mark had said. So I really want to thank the teams, including the ULA launch team, that really got us there today. Really just amazing. The Orion was great. You know, just a very, very clean flight. A few things that were not really unexpected. Our video processing unit reset a couple times. We kind of expected some of the avionics to go through resets. I think we had talked to you about flying through the Van Allen belts and seeing higher radiation than we had seen for a while. You know, we have to go look at that. When we get to Naval Base San Diego, we'll actually get into the capsule and we'll get those flight data recorders that have that high data rate developmental flight instrumentation that we call it, all of that data. And we're going to actually act to try to get that to one of our facilities there in San Diego so we can start processing that data and get it to our engineering team and the NASA team as soon as we can. So that'll be a big deal. But from the The operational data that we saw today, the ship just flew extremely well, and the flight ops team in Houston really only had to interact with the system a couple times as we went through the day. So it was really a terrific performance. You know, we've talked before, we're already working on that next capsule. We're already forming metal parts, machining parts. We've already sent some parts to ESA for the service module work that they're doing for the next time. So there is an awful lot that is already going, but we'll learn just an enormous amount from what we did today, and when we get all that data back, that will be a big deal for us. You know, we talked a little bit, some folks have asked me what made me nervous, and I went through a couple times and talked about separation events and talked about making sure we got the full burn. So Mark picked out a couple moments. I would say that seeing the fairing jettison was a big one for me today, actually. Being worried about all of those separation events for months and seeing those come off so cleanly was really extraordinary. And then have the upper stage burn that put us on the reentry trajectory absolutely right on the money was really great. But I would also pick on that video feed, and that was something that personally I've really been looking for, is that view so much further than the space station orbit than we've been. And that was really unique to see that. So I'm looking to see more of that when I actually have time to sit and watch the replays. Not quite sure when that's going to happen, but and I would just like to close on one particular thought. Bill and I have been at this a long time together. When we started at JSC, we started with all the Apollo guys still there. So we've kind of now finally done something for the first time for our generation. It's a good day.
Yeah, I'd like to echo the comments I've heard already, and it was just such a pleasure to witness the inaugural flight of Orion. It's an amazing vehicle, and the fact that it went so well is a testament to the workforce that put in so many hours and years of hard work to make this work well. I think one of the memories I have of today's flight was, you know, the Earth limb view was amazing, but I think it was the first video that came down of the Earth, and it wasn't something I didn't recognize. It was something I recognized, that view of Earth. It just looked familiar, but then it struck me, that's not from a platform I'd been on before. That's from our Orion spacecraft, and that really meant something to me. So that was just amazing. And as impressive as this flight was, this was just serial number 001 of Orion. And as successful as it was, there's just great things more to come down the road, and we're looking forward to that. And I can't wait to get back to work. You know, serial number 002, that one's going to be on the Space Launch System. And I tell you, the sight of the Orion on top of the Space Launch System is going to take your breath away even before it takes flight. And then when it does take flight, America's going to sit up and take notice that the space program is just incredible and it's full of vitality. And then we'll go on there from the second flight to the third flight, and that has a place near and dear to me because our crew is going to be on board. So there'll be 4 astronauts on board the Exploration Mission 2. And the neat thing is that this vehicle is not destination specific. It's going to go to a bunch of different places. We all know the amazing places it can go to. We talked about the lunar vicinity, to an asteroid, and maybe to Mars one day. And the neat thing about that is this, like I say, is serial number 001 of a storied fleet of vehicles. And when we look back 20, 30 years from now, we can trace it all back to today, where it started out with Orion serial number 001.
Okay, thanks. We'll take some questions, and if you wouldn't mind stating your name, affiliation, and to whom you're addressing your question. Let's start on this side.
Hi, Clara Moskowitz for Scientific American. Just a quick clarification. When you mentioned the reset of the video processing units, was that definitely caused by the radiation, or that's what you're thinking?
We don't have the data to know that for sure, but we fully expected that we'd see some of the avionics boxes go through resets.
And can you talk a little bit more about the performance of the heat shield? Did you get any data in real time about how that was going?
Yeah, the instrumentation for the heat shield is part of this data that we record on board. So we'll get that down, and we took some photographs, which they're probably starting to look at now. So the first time we really get a chance to look at it is when it gets on the ship in about 4 hours. So we know it worked, but the specifics of how well and what are the subtleties, it'll take more time to investigate. Yeah.
Irene Klotz with Reuters. On the radiation issues, again, did you have any indication at all that you did have any of the computer resets that you had talked about a little bit before flight?
The only resets that we saw were in the video processing unit, which the flight computers, to my knowledge, we didn't see any issues with. But they're somewhat similar boxes. In fact, we use the video unit as a backup memory for the flight computers. So.
Hi, Miriam Kramer with Space.com. And not to take away from the celebration of the flawless test flight, but I'm just curious, what kind of things can you learn from this kind of really amazing test flight that you maybe didn't know before, it was on the ground? Like, is this the kind of thing where you really wanted to stress those systems and even see them break, and you could get more data that way? Yeah, I mentioned a couple days ago that it's an unmanned test flight, and you have to take advantage of that. So you push the systems, you push the operations that you're the most worried about. And again, we have great models and some of the best people on the planet on these systems, but until you fly it, you don't know. So we didn't see anything major, that's clear. It looks like it flew very close to what we expected. But we have 1,200 sensors, thousands of pieces of data that we're going to get back, and I'm sure we're going to find some very interesting things about how it behaved, and that's really important for us as we get ready for the next mission. So
you also gain a lot of data that you can't really get from testing. So just being in the environment, like the GPS system, the global positioning system, at this high apogee, how well it would work, how many satellites it would actually acquire. We have theories, we have thoughts, but it's a function of actual margin through the antenna system and into the receiver, and a function of the GPS constellation. So that you can't really test. How the vehicle actually flies, we have pretty good computational fluid dynamics to see how it actually performs, how it dissipates heat, energy, what lift vector, what control we can do. They did a little lift maneuver with the thrusters. So all that stuff you could get a good understanding, but this gives you a data point that anchors your models, that says, hey, now these models that we had before aren't exactly right. So there's definitely some things, because I would hear the folks on the loops talking about stuff, how the cooling system was working. They saw some things every 15 minutes was a little different to them. It's just a function of how the vehicle works. You could see the capsule expand as it went to vacuum, so you can see the pressure change inside the capsule, and that's a normal thing. We knew that from shuttle, but then you get to actually see the real numbers with Orion. So it's those real-world environmental complex interaction kind of things that you can't test anyplace else other than to go fly.
And we actually saw things, subtleties that we didn't think about because we didn't talk about as much about the big events in the mission. But, we watched the capsule fly herself. And you watched the thrusters fire, so you watched all the individual thrusters fire. You saw the propellant use, and you saw how it went to attitude prior to like the maneuver burns that Bill talked about. So there's actually a great deal of data we got just in the operational nature of how the spacecraft flew.
Hi, Robert Perlin with CollectSpace.com. There was a lot of excitement in the press room when it splashed down, so it was a little hard to hear some of the details. So if you could go over some of the recovery, what we know about the recovery, in terms of did you get all three main parachutes, the forward bay, and what might have happened with the uprighting balloons? Not that they were needed, but
yeah, good question. So the crew actually now remember we had an option, if everything was going well, to sit in the water for 60 minutes and let the systems run, and we were measuring the thermal soak back. Basically, heat shield's obviously very warm, and we wanted to see how that thermal properties soak back into the cabin and how other systems were affected. So we let it do that. So the recovery guys did not go near the capsule for 60 minutes. In fact, I think they just started 30 minutes or so ago to go recover the capsule. We did have them out looking for the forward bay cover and to get the parachutes. The mains were an objective, so we got two of them. Two of the mains were recovered. We knew they sink pretty quick. They're not part of my in my budget. I didn't assume we'd get them back, but we tried to get them so that we could. Sometimes you learn things with the risers and other things that you wouldn't see if you get them back. So we got two of those back. Forward bay cover sunk. If you saw it before we put it on, you realize how big it is and how heavy it is. We were hoping we might get some of that, but we didn't. We'll see, though, on the front part of the CM whether there are any issues with the recontact. Not that we've suspected that happened. As relative to the CMIS bags, a couple, at least one, did not deploy at all. We know one was underinflated, so we're actually looking at the data today. We know that the pyros fired. and the bottles are empty. So what happened with the rest of the bags is part of what we're looking at. But that's, again, a great part of the test. So this one system behaved a little odd, shouldn't have done that. We did land stable 1, which was good. We landed with the heat shield down, and the riser cutters fired, so the parachutes did separate, all the things that we expected to happen. So.
Hi, Ken Kramer for Universe Today in America's Space. First, congratulations to everyone. My question is, I wonder if you have heard anything from the President or congressional leaders, and are you hopeful that you will at least get continued and support and even better increased support so we can move a little bit faster? Thanks.
Well, we know we had Senator Nelson was here, and I know on the Twitter feed we've seen some senators and congressmen send their support. So I think just the beginning. We've been busy with other things, but I expect we'll see that a lot of attention relative to that. So we've already had a lot of support. You think about it, you know, it's a bipartisan program. This whole SLS Orion ground ops program is supported by both. We've always believed, and I think with that bipartisan support, you see it, that this is an important part of keeping the United States as a leader in space. And so I think a successful test flight just helps that kind of discussion, I think.
Yeah, I think we didn't get anything. I mean, we got general congratulations from a lot of different folks. It was kind of fun. I got a picture from the service module team in Bremen, who's working on the service module for EM1, and gave us their high congratulations and said they were busy working on the service module for us today. So that was good news on multiple fronts. So that was good. I think the other thing to really watch too is you sometimes don't get to see all the work behind the scenes that goes into this flight. So, you know, you need to take a look at what's coming up in future activities. There's a lot of work going on in MAF with SLS that you ought to try to follow. We'll try to make available to you that you can actually see what's happening. We've got the flight dome down there. We'll start some flight welding in January. We've got the shuttle main engines down at Stennis that will actually look at start box condition stuff probably after the first of the year. So that activity is big. We've got the solid rocket motors that are going to be on the SLS firing next year. As Mark said, they're busy machining all the forgings and the key aluminum pieces for the next EM1. Those start getting assembled in MAF fairly soon, I think next year. And then I think the actual welded Orion ends up in Florida by the end of next calendar year here to begin. So EM1 will be here as a pressure shell coming out of MAF by the end of next year, ready to get ready for EM1. So I think sometimes we forget. We see the big event where we can all watch the launch, but then we don't see all this other work. So we're going to try to do a better job of exposing you to what we're doing. Because when I look across what this team is doing, the progress that this team is making across the board is just absolutely phenomenal. I am so impressed with the amount of work that this team is pulling together as a large team to really make this stuff happen. Is just phenomenal. So then we'll try to get that message out, and we've been getting good support, and we'll try to increase the support as much as we can. And I think I get a hearing next week, so I'll get a chance to try to cheerlead a little bit next week in the hearing. So we'll see how that goes. We'll see if we get applause in the hearing or I get the normal press welcome.
Hi, Emily Carney, AmericaSpace.com. Apollo did not have the use of real-time cameras and drones at the time to monitor reentry in the initial stages of vehicle recovery. At present time, how significant would you say has this technology been in today's continued recovery operations and obviously monitoring the vehicle's performance?
A couple things. So you saw some of the really cool views that we were able to send down, but we also have high-speed cameras in locations like watching the parachutes that are recorded data. So I think high-speed video has been a huge part of our test program, including the pad abort test we did. It was enormous to see separations and the subtleties that go on, so that's huge. What you didn't see was we also had two P-3 aircraft that were following the entry, one measuring the heating on the heat shield so they can actually measure temperature of the heat shield coming in, and the other are following separation events like forward bay cover and everything, taking pictures. So it's huge. I mean, the seeing the pictures yourself is a huge benefit to the engineering team. We're going to get a lot of instrumentation, but when you actually see the operation itself, makes a big difference. And of course, it was also really, really cool today. And I want to thank the ICONA team especially. Yesterday there were some problems. We had fog, it dried, and they couldn't get off the ground early enough, and they had some other things. It was no fault of their own. And I understand they actually worked, they had some technical issues and worked overnight to get that ready for us today. And I want to applaud their efforts because it really helped, I think, put the exclamation point on the mission to see that capsule coming in as fast as we expected it would, and then to see the parachutes deploy. There's really not been a film of that kind of deployment before, and it really gives you a sense for how dynamic that phase is. So I think it's huge.
Amy Green, WMFE Public Radio. I just wondered, I realize, of course, it will take a long time to go through all of the data collected from this mission today. So far, in just the short period since we've had splashdown, what is the biggest anomaly you're seeing already, or what is the most interesting thing that you will be immediately looking at after the end of this mission? And also, just another quick question I wanted to ask about the Orion capsule's transportation back to Kennedy Space Center. I think I heard that it's going to be trucked back, and I just wondered what are the security or safety protocols for that? How will that work?
It will be trucked back. That is the plan, and the ground system development program here at Kennedy is the agent for doing that transportation, and so they've actually gone through and secured all of the transport permits and everything, because you have to do that state by state by state all across the country, and there are unique rules in every state for large hazardous cargo. The craft will still be fueled. It will still have hazardous materials during its transport. So they have worked all of that, the security aspects and the transportation aspects. We expect to get the capsule back here close to Christmas. Would be what the plan would be.
I think the key, rather than picking on anything that acted strangely, our big focus now is to get that data from those 1,200 sensors, and the team is so they can pore over it in the next month or so, because I think that's where we're really going to see things that tell us, as Bill said, tell us about the environment, tell us about how the vehicle behaved, and that's the focus of the team in the next few months.
Let's go to Gina Sinceri, and then we'll go to Frank Mooring.
Gina Sinceri, ABC News. Were there any aha moments for any of you during today's mission? That's something that surprised you and you went, I didn't know that would happen.
We were talking earlier about whether you would let yourself hope that it would behave so well before the flight, right? Because actually you want the team to be trained to handle when it doesn't go very well, and so they can handle issues and work. And when we sim this a lot, we simulate these flights a lot, and we simulate failures, so the team is ready. So there was a bit of an aha that it worked so well today. And that's it's a great team. It's a fantastic team. So it doesn't surprise me that this team puts out quality work, because they do it every day. But in that environment and how difficult this test was, that it flew right down the middle. I mean, that was a very pleasant relief. But they did a great job.
Yeah, I think for me the thing that's kind of fun is I understand all the math and all the trajectory stuff, but then to actually see it in real time and see the plots, to see us go from apogee to the really high perigee, the 31,000 kilometers, to actually see that occur and see how fast that's occurring with that Delta IV upper stage really pushing us. And then when you get to that little peak at apogee, spacecraft's flying fairly slow, so that's a fairly long period of time, and then you start to descend down, and the perigee now goes negative, right? So when you're doing that burn, you're actually targeting for below the surface of the Earth. So to really see that in the plot and see the capsule and see the images and then tie that back with the math that I know from all my engineering, putting all that together in one time is maybe not an aha moment, but it's, for an engineer, it may be as cool as an artist appreciating fine art in a museum, right? It's the same thing when you see all the math and all the numbers, and you see the visuals, and you see the data, and you see the plot, and you know it's a real spacecraft. All that coming together is pretty special.
Okay, let's go here.
Yeah, hi, Craig Cavalt with Aerospace America, and I'm going to ask a grumpy question because Bill and Mike have had so many in the past. A question about the future of the heat shield design. Is the program definitely going to shift from a honeycomb to a monolithic design? And has that been caused by problems with the Avcoat material being applied in an uneven manner?
So we need to get the data from this test before we make any final decisions on the heat shield, because now we've actually flown it. There are things we saw in the manufacturing of the heat shield relative to strength of materials that was a little less strong than we expected it. And for EM1, we needed to make some modifications. We want to understand what happened when we built this last one and look at options for improving it. So that's been work we've been doing since we built this first heat shield. So we'll take that data, we'll take the data from the flight itself, and we'll put it together and make a recommendation as to what to do next. The team, there was no issues as far as unevenness of the heat shield. It was built exactly to the spec, and it's a beautiful piece of manufacturing. But there's something about the material that wasn't quite as strong as we expected in tests we had done before, and so we have to resolve that issue. So when we get to the resolution of that, that'll tell us if we need to modify the design. It might be it's just something we need to do a little bit different about the mixing or how we apply it or how we cure it, something that simple, and then we could have the same heat shield we have today. So,
and I think the other thing we're trying to do here too is, we're trying to build a system that's manufacturable and fairly easy to reproduce, again, because we want to keep our operating costs as reasonable as we can, so we don't end up with each spacecraft being, totally unique from a manufacturing standpoint. So we use reaction friction stir weld where it makes sense. They're going to change some of the wiring based on what they learned down here at Kennedy of how you actually lay the wiring in the capsule. So I look at these as pretty positive changes as we actually learn things that are different and we can get better performance out of a different maybe heat shield material. Mark may also get better manufacturability out of a different heat shield design. Mark will trade that. We may even change heat shields even after EM1 or EM2 somewhere in the future, if depending on what the reentry velocity is and what we learn from this test. So I think we need to not think we're getting to the perfect design and then it's not going to change. We're going to be smart enough and nimble enough we can make small changes to keep production costs down and keep our reliability up to keep us with a really safe system. So we'll keep doing those things, and I think we'll learn really a lot from this test as Mark described, and we'll make Mark and his team, whenever they're ready to make those decisions, we're ready to support those decisions.
Yeah, Mike did a real good job a couple of days ago when he talked about we've looked at some of the primary structure, and as we built one, we found a way to actually make it out of fewer parts, right? That helps the cost. We know we've done things to make the structure lighter because we built one and we knew how to do that. Like I mentioned before, the barrel for EM1 is 25% lighter than the barrel for EFT-1. So those are the kind of things you do all the time. You're improving performance and because of what you learned, either by flying or by building it. So.
Yeah, this is James Tutton with Spaceflight Insider, and I just have a question, well, two questions. One, are there any physical tests that are going to be done on the spacecraft before it gets to Florida, like looking at the heat shield, taking samples, or anything like that? And my other question is for Rex. What if some of your fellow astronauts had to say about this vehicle, like as it pertains to like being inside and wanting to fly on it? Thank you.
I'll take the first part, and there's a couple aspects of it that we talked about, getting the data recorders out and being able to process that. We also we have a request from the engineering team to try to take some samples, plugs out of the heat shield. So we're looking at how that fits into the timeline and how many of those we might be able to do. There's a lot of inspection, documentation, photographs, everything of the actual heat shield when we get. But we also need to get it on the road and get it back here for a much more thorough assessment.
You asked about what the astronaut office thinks, and I think you'd be hard-pressed to find an astronaut, past, present, or future, who wouldn't love to fly in Orion. I mean, this is the true exploration that we live for, and it'll be really exciting to have a chance to get on board one of these vehicles.
Okay, let's take a couple more if there are any more. Let's go on the third row here.
Jackie Goddard for the Times of London. To what extent is the future timeline and evolution of Orion and SLS and where it's going and what it'll do dictated by budget? And if you had a greater budget, to what extent could you speed that timeline?
I would say so. It is driven by the budget. But we recognize, we recognize where the budget is, and there's a lot of priorities in the country. And so I frankly feel blessed that we have the budget we do, and we have bipartisan support for the pieces for SLS, Orion, and ground ops. And we need to make the best use of the money we're given. You can see an example of that in that with the DDT, the development budget we were given, we split our development kind of in 3 phases. So EFT-1 is the beginning, and it's mostly crew module work, structures, heat shield. EM-1 adds the service module, adds more avionics, and starts doing qualification. Then EM2 adds the life support, the displays and controls, the seats, the things that the crew interacts with, and qualifies the full system. So we had to break it up into 3 pieces, and the schedule is part of that, right? Then the next flight on EM1, and then EM2 in 2021. That's absolutely driven by the budget.
And what's, from my perspective, I look at kind of human spaceflight as a whole. So there's a lot of pieces of human spaceflight, right? There's the International Space Station, right, with our crews that are going up to space station, and they fit in the exploration puzzle because, we're learning how the human body performs in space. So when we take crews on missions of 3 years or 2 years duration, we'll understand from space station how the human body performs. Next year we have the 1-year expedition on board space station. We also get to check out like long duration life support systems that can operate with very low maintenance for multiple years. That's part of space station. Then there's cargo that needs to go to station, crew that needs to go to space station. We've got those activities going on. We've got SLS, we've got Orion, ground ops. So human spaceflight is a pretty broad portfolio. When you look at the sum of all those, probably none of them are really funded at the optimum level that they would like to be as individual programs. But if you look at it as an overall human spaceflight program of what we're doing in low Earth orbit, we call it the Earth-reliant region. Then we're going to take crews out to cislunar space. We call that the proving ground region. That's where we're going to learn to operate away from kind of the protection of being hours away as we are on space station. And then eventually we need to get Earth independent, which is a Mars class mission. So even in my directorate, we're funding things that are sitting on the Curiosity rover today. We're measuring the radiation environment of Mars so crews will understand what it's like to go there. We're going to carry a in situ resource utilization experiment that will pull oxygen out of the Martian atmosphere and actually condense it or compress it into a bottle, so we see if we can actually use some of the Martian materials to go push crews into space, so we don't have to carry everything with us. And we know there's water on Mars. We can electrolyze water. We'll use that. So when I look at this, it's this whole portfolio of exploration, and it's tough to pick any one favorite piece and push that piece at the expense of the other. So we've got to look at it as a combined portfolio, and I think we have a really robust overall plan that's going to move us at a reasonable pace as fast as we can with human presence into the solar system.
Okay, let's take a final question from Frank Mooring.
This is Frank Mooring with Aviation Week for Mike and Mark. Is there any way to characterize the amount of data that's still stored in the capsule in terms of gigabytes or something? And also, could you sort of walk through how you're going to distribute it, what the schedule and the process is for distributing it, and whether there are particular data points that you're going to try to pull out early? And finally, if you know, did the P3 get the IR data on the long distance? Thanks.
Haven't heard about the P3, although we know that they acquired.
I did hear that they did. Yeah. They followed it all the way to the ground, so we'll see what the data looks like. Yeah.
So we talked about the DFI. There were 1,200 sensors in that DFI. Now, most of that data is sampled at a much higher rate. The normal operational instrumentation is usually on a 1 cycle a second, 1 hertz rate. The DFI data is typically at a much higher sample rate, so that we can really pinpoint some of the phenomena that do that. Our schedule to get the data, we actually, per the terms of the contract that NASA had with us to do the test, we owe them a report in 90 days after today. And so that's why we want to get the data and get it out of the capsule as soon as it's back to port. And start actually working on that data. And as soon as we have the data processed, we'll be sharing the data with NASA, but then we will be doing our own analysis of that data and what it means for these individual systems. That'll be the core of that report that we have.
There's actually experts on the ship. We have thermal protection system experts, computer experts, forward big cover experts, pyro experts. So they're when this thing gets on the ship, they're going to be looking at it right away, kind of at a macro level. Hey, this is the kind of things we see. But as Mike talked about, that data in those computers is really the key in seeing specifically how it experienced the flight.
Okay, well, that's all the time we have today. I'm also told that the White House congratulated the team at the start of a president's briefing today. Let's take a look at the highlights from today's flight test. And again, just want to thank everyone for joining us.
Beautiful morning for a launch in Florida.
AC is go. RC. Clear to proceed. Launch director. This is the launch director. You have permission to launch.
Five, 4, 3, 2, 1. And liftoff at dawn, the dawn of Orion, and a new era of American space exploration.
Just a few miles away from reaching peak altitude. Again, this dramatic view of the limb of the Earth from one of the flight test cameras in the crew module of Orion.
Hi, I'm Peter Cullen, and you're watching NASA TV.
On launch day, before the actual launch of the Orion takes place in Florida, the Icana will take off from NASA Armstrong Flight Research Center and head out to the Pacific to acquire the Orion capsule on re-entry and look at the parachutes as they come out. So we'll be at an altitude that when the Orion capsule is coming in, it'll be coming towards us. as it's going down.
865, how's this climb rate working for you?
We're going to use the infrared camera to acquire the vehicle as it's coming down and eventually change to the optical camera to give better situational awareness of what's going on splashdown. Ikana is a Native American Choctaw word that means conscious, self-aware, intelligent. And the reason we chose that name for the airplane is that we were interested in doing research in autonomous control in ways that the airplane could assist the pilot in avoiding collisions or avoiding traffic and being able to respond to its own environment in a safe way. The agency has used the Ikana UAS in several different ways. Ikana supported the Western States Fire mission. The goal there was to provide situational awareness to the firefighters in the middle of fighting a fire and do it in almost real-time manner, something they had not been able to have from the air in the same way.
Okay, we're leveling off at 12,000. Our first tense point is going to have us around 80 knots.
We've also flown fiber optic technology on the airplane to measure the wing bending on the airplane.
Push over, pull up.
With the fiber, they could measure like hundreds of times more of what the wing was doing. So if you want to have the feedback to what you want the wing to do, either by bending the wing or bending other surfaces, you have way more feedback by doing it this way.
Oakland Center for Hawk 2-1. It looks like I'll be overtaking traffic. My nose for about 3 miles. I'd like to deviate right.
Right now, we're getting ready to fly the airplane with a research flight control system that will allow an eventual autonomous capability of the airplane, primarily for self-separation. Our goal is to improve the safety of UAS flying in the national airspace, and if we can help the pilots on the ground controlling the remotely piloted airplanes know where the traffic around them is and give them standard ways to separate from that traffic, this would be a great way to do that.
Oakland Center, I got a traffic advisory saying that I have 02 Sierra overtaking. I'd like to deviate right for traffic.
Hawk 2-1 approved as requested.
During Orion's flight test, the spacecraft will travel 3,600 miles into space, return to Earth at speeds of up to 20,000 miles per hour, and endure temperatures near 4,000 degrees Fahrenheit before splashing down in the Pacific Ocean. For the team tasked with recovering Orion after splashdown, this is when the work will begin. NASA's Ground Systems Development and Operations Program, Orion prime contractor Lockheed Martin, and the U.S. Navy have worked hard to prepare, practicing recovery operations during the past year to establish techniques they will use to recover Orion, the parachutes, and the forward bay cover from the water.
We're working with the Navy to figure out a way to use these well deck ships that they have to get the capsule back in the well deck and allow the crew to get out basically on dry land in a sense. And so all this testing is about how to make that work.
Before Orion launches on its flight test from the East Coast, the recovery team on the West Coast will embark aboard the U.S. Navy's amphibious ship, the USS Anchorage, and head out to sea. All of the necessary hardware and equipment will be carried below in the ship's well deck. It also is where Orion will be secured after the team recovers it. While the team waits for Orion to take flight, they will launch weather balloons from the deck of the ship and monitor sea conditions. Meanwhile, about an hour before splashdown, helicopters will take off from the ship's deck and fly out to help locate Orion as it makes its descent toward the ocean. The helicopters also will help the team track Orion's protective forward bay cover and parachutes for the recovery. Teams in rigid hull inflatable boats will find and secure the hardware with floats until they're able to safely recover it. Minutes after Orion splashes down, the crew module uprighting system will inflate to help stabilize the spacecraft in case it doesn't land heat shield first into the water. U.S. Navy divers in Zodiac boats will check for any hazards around Orion. Then they'll attach a sea anchor, load distributing horse collar, and tether lines to the crew module and work to guide it to the ship's well deck.
So it's our way of recovering the Orion crew module, and we do it in a way that we protect the heat shield so that we can get as much good information as we can for the engineering analysis that we'll do moving forward.
The spacecraft will be set down on rubber shock absorbers secured to the deck, and the ship will head toward calm waters. The crew module will then be put into its recovery cradle and readied for offloading. The ship will then begin the journey back to Naval Base San Diego. The team also is prepared to use an alternative method of recovery in case Orion can't be recovered using the ship's well deck. At sea, a sling will be placed around Orion, and the stationary crane on the USNS Salvor, a salvage ship, will be used to lift the crew module up and onto the deck where it will be secured. It will remain there for its trip back to port. In case of very turbulent sea conditions, the USNS Salvor could tow Orion along until calmer seas are reached and it can be recovered. When Orion splashes down in the Pacific Ocean, the U.S. Navy ship and recovery team will be ready to recover the spacecraft and safely bring it home.
My name is Tara Radke, and I'm the System Manager for Orion Integrated Landing Systems. So, even though Orion has performed the majority of its mission of taking humans to space and then returning back home, we still have to do the last really important part, slowing down so that they can safely land and be recovered onto the ship and back home. Orion's coming back from deep space and re-enters the atmosphere, going really fast. The guidance navigation control system does some maneuvering to help slow down the vehicle, and at that point, start looking for the right conditions to deploy the parachute. The first parachutes that come out are the 4-bay cover parachutes. They're mortar deployed, so they're fired basically with cannons out the back of the vehicle at 125 feet per second. After those are inflated, pyrotechnic piston thrusters push the cover off and jettison it away, and that exposes all the other parachutes that are on the top of the vehicle so they can perform their job. The next parachutes in the sequence are the drogue parachutes. The drogue parachutes, again, are also mortar fired out into the clean air so that they can properly deploy, and they actually open in stages, so they slowly open up so that they don't have a hard force on the vehicle or on the parachutes themselves and damage them. At that point, we actually cut the drogue parachutes so that those parachutes are able to leave, and the next parachutes, the pilot parachutes, are able to deploy at that point. The pilot parachutes are small chutes. They're actually 11 feet in diameter and are actually used to pull the main parachutes out of the bay. The main parachutes are the large ones. Those are 300 pounds, and when they are fully inflated, 116 feet in diameter. The main parachutes do the majority of the job of slowing down the vehicle. All 3 main parachutes deploy. They also open in stages to protect the structure in the parachutes and the crew on board. And at that point, slow the vehicle down to about 25 feet per second when it lands in the water. Working in the descent and landing phase is really challenging. You're coming from extreme environments that you've had to go along on the ride the entire way. As we work with the parachutes, as we work with the GNC team and how all these pieces fit together, it feels like a very important job to make sure that we're taking care of the crew, that we're bringing them back safely, and that we land and keep the vehicle safe around them and are able to recover them safely. Hi, my name is Molly White, and I'm a heat shield engineer for Orion. The Orion spacecraft is designed to go further than humans ever have before. And the further out you go, the faster you come back. And the faster you come back, the hotter you get. So Orion needs a really, really good heat shield to protect its crew from that really, really hot air that's going to be around it when it comes back. Why Orion needs a heat shield? If we think about friction, and I'm moving my hands past each other, just moving them pretty slowly, I can still feel heat build up between my hands. It gets hotter. Well, if we think about Orion, which is going 25 to 30 times the speed of sound, it has that same friction with the air, only it's going way faster than my hands can. So there's a lot of heat that is around Orion that it needs to be protected from. The heat shield for Orion, it's 16.5 feet in diameter. It's the largest, most innovative heat shield of its kind. The heat shield weighs about 1,000 pounds. The total vehicle mass is about 20,000 pounds, so it's about 1/20th the weight of Orion just for the heat shield itself. So Orion, for its first flight test, will see surface temperatures at around 4,000 degrees Fahrenheit. So we've developed new materials for Orion that can withstand those higher temperatures. The material for Orion is actually designed to withstand up to 6,000 degrees Fahrenheit. My favorite part of working on Orion is just the fantastic group of really, really smart people that I get to work with every day. They're excited and passionate, as I am, about taking humans further than we ever have before, bringing back all the technology and everything that we've developed out there back here to Earth just to improve our lives. And that's the thing that I get most excited about when coming to work.
My name is Jude Moranci, and I'm the Mission Planning and Analysis Lead for Orion. So Orion fits into the overall exploration architecture by being the vehicle that really gets the crew safely to and from Earth and can provide for them for 21 days worth for up to 4 crew of supplies and breathable air and things like that. We're really designed to be the first stepping stone to a wide variety of missions. We can go to asteroids with the crew, and we can go to Mars, and those things all need more equipment, but Orion will be that first piece, and we'll be able to support a lot of missions in whatever the plans for exploration are in the future. So in order to be versatile, Orion is treating it like upgrade kits. It's almost a plug-and-play system, where right now we're building the base vehicle, and that's what essentially we're flying on EFT-1. And then for follow-on missions, we can keep adding to it. We can add the docking system, we can add a water kit to extend a mission, we can add thermal protection. We could change the heat shield to make it thicker, which would handle a higher speed entry. And really what you need when you go beyond is to add a habitat module to Orion to give the crew enough space. So all of these things we can modify over time and build up and take away as needed as technology improves as well. So what I like best about working on Orion is we're building the exploration vehicle. So, I mean, I grew up watching the shuttle, and I worked on the space station, and all of those are in low Earth orbit, but for me, it's we're really going to go beyond. No one's been higher than a few hundred kilometers from Earth in my lifetime, so I'm very proud to be a part of sending people beyond low Earth orbit again.
Yes, my name is Lee Morin, MD, PhD, and I'm a astronaut mission specialist. Well, with Orion, America is building a new spacecraft for exploration. Could involve missions to the moon, missions to an asteroid, missions to Mars, and we want Orion to be able to do all those things, to take 4 astronauts into deep space and return them safely to the Earth. And the goal was to build a cockpit user interface, a dashboard, so to speak, that would allow the crew to control that spacecraft for that period of time for these deep space missions, and to have the flexibility so that even if they were away from the planet for months or even years, that they would have the information they needed to fly that vehicle and return safely to the Earth. And the concept was to go with a glass cockpit, and what that means is that the instruments are all images on a computer screen. They are all on the glass. So rather than flipping a physical switch, the crew brings up a computer screen and flips a virtual switch, a little icon of a switch or icon of a valve. And with the exception of 7 panels right around the computer screens, which have about 60 switches, that is all of the cockpit of Orion happens on the glass. One big benefit is a weight savings, because you don't have to have a physical switch. And having a physical switch, not only is there the weight of the switch, but you also have the weight of the wire to the switch. and you have to have the weight of circuitry that takes that wire and feeds it into the vehicle computers. By putting that on the computer screen, you save that weight and you save the complexity of those wires. That gives us a lot of flexibility, and as we work with the cockpit, if we find certain ways that we could do it better, it's perhaps easier to update the software than it is to rewire the vehicle. It's been very exciting to see the Orion and the cockpit come together and to see the computer software that I've helped write and my colleagues have been writing come together, and think that these are the screens that the first crew that goes to an asteroid will be looking at to help them control the vehicle. These are the screens that the first humans who go to Mars will be looking at as that mission unfolds in the decades ahead. The Orion is going to be the linchpin of humanity's exploration beyond low Earth orbit into deep space. I get a chill thinking about the role that I've had and the privilege I've had to be able to participate in that.
We explore to gain knowledge, to push the boundaries of possibility, and to reveal the unknown.
We seek to discover, to find answers here on Earth and in space.
Was Mars once an Earth-like planet with water and an atmosphere? What happened? Can the same thing happen here on Earth?
What about asteroids? Is there something we can do to prevent them from colliding with Earth?
We can go to Mars in our lifetime and answer some of humanity's fundamental questions about life beyond Earth.
Robots are doing great work exploring our solar system, but eventually, we want to be able to put a person on the ground.
Now, sending people to deep space destinations requires a lot of stuff. Food and water, shelter, fuel, spare parts, tools and supplies. It's like a spacefaring RV. The farther you go and the longer the trip, the more you need, and that means moving a lot of mass.
So when you talk about getting past the pull of Earth's gravity, you need a bigger, more powerful rocket.
The Space Launch System is an all-new heavy-lift rocket that uses a combination of proven hardware and technology to make it more affordable. We could take the best from all we've learned from building rockets and combine that with cutting-edge tooling and manufacturing technology to build the most powerful rocket in history.
You can fly to really high orbits around the moon with this rocket without requiring any other assistance. But when we add an upper stage, we'll have an even bigger capacity.
The larger evolved version of SLS can carry a habitat, larger solar arrays, additional propulsion, you name it. It's really a versatile rocket.
To get the astronauts beyond low Earth orbit, we need a new crew vehicle, Orion.
The Orion spacecraft is a conical shape, like Apollo was. But it's actually larger than Apollo and is capable of taking people farther into space than ever before. It can protect a crew of 4 for up to 21 days and carry food, air, water, supplies, all the things the crew will need.
Orion is the most advanced and versatile spacecraft ever made. It uses state-of-the-art technology, materials, and design processes based on more than 50 years of research and technology development.
Flight crew, close and lock your fire.
The first crewed flight of Orion and the Space Launch System will be a flight around the moon during Exploration Mission 2. A crew of astronauts will launch on SLS, fly several orbits around the Earth, then perform a translunar injection, which will send them on a path from Earth orbit towards the moon.
Once the crew gets near the moon, Orion will pass within 60 miles of the surface. And from there, Orion can insert into a high lunar orbit, several thousand miles from the surface,
the knowledge and the experience that we have at our disposal today come from nearly 50 years of space exploration and ultimately benefit lives here on Earth.
Who knows what will come out of the scientific knowledge, discovery, and economic opportunities that result from deep space exploration?
We just hit the tip of the iceberg in terms of human exploration. Now we need to explore deep space. To me, that's the goal, to expand humanity's presence beyond the Earth.
Exploring beyond has a deeper purpose, and it is a bolder mission than anything we've ever done before.
I believe that people still look to NASA and the United States for leadership in space.
It takes courage and resolve and commitment. And when we leave Earth to explore our solar system, it will not be as any one nation or culture, but as citizens of Earth for all of humanity.
Orion is getting ready to launch. My name is Kelly Smith, and I work on navigation and guidance for Orion. Orion is NASA's next-generation spacecraft. Built with versatility in mind, it can take astronauts deeper into space than we've ever gone before, to an asteroid or even onto Mars. For these missions, Orion has to be one tough spacecraft, withstanding high speeds, searing temperatures, and extreme radiation. Before we can send astronauts into space on Orion, we have to test all of its systems. And there's only one way to know if we got it right. Fly it in space. For Orion's first flight, no astronauts will be aboard. The spacecraft is loaded with sensors to record and measure all aspects of the flight in every detail. It all begins with launch aboard a Delta IV Heavy rocket. As it punches into Earth orbit, Orion will jettison its launch abort system. The abort system is a safety feature designed to pull Orion and its crew out of danger if there were a problem with the rocket during ascent. Orion's journey is just beginning. As the spacecraft and the upper stage begin their first lap around Earth, Mission Control in Houston is monitoring the progress of the flight. Orion's over 100 miles up and going about 17,000 miles per hour. Just as it passes over the Indian Ocean, we lose communication. This is expected. The communications link we have through satellites to Orion is momentarily lost, but Orion continues to receive and process data. Its computers can handle 480 million instructions per second. Imagine you are traveling with Orion as the flight test continues. One orbit completed. Time to go. The upper stage of the rocket fires again. Like the setup for a roller coaster ride, this is the big climb we've been waiting for. We are headed 3,600 miles above Earth. 15 times higher from the planet than the International Space Station. As we get further away from Earth, we'll pass through the Van Allen belts, an area of dangerous radiation. Radiation like this could harm the guidance systems, onboard computers, or other electronics on Orion. Naturally, we have to pass through this danger zone twice, once up and once back. But Orion has protection. Shielding will be put to the test as the vehicle cuts through the waves of radiation. Sensors aboard will record radiation levels for scientists to study. We must solve these challenges before we send people through this region of space. For this flight, it's time to head home. The upper stage of the rocket triggers separation. Orion's jets fire to turn it into the proper position to re-enter Earth's atmosphere. No matter what happens now, we're coming in. 75 miles above Earth, the spacecraft enters the atmosphere. Things happen quickly. We're now traveling more than 20,000 miles per hour. Air particles pushed out of the way heat up. An envelope of hot plasma surrounds the vehicle as it plummets towards Earth. The plasma reaches temperatures of 4,000 degrees Fahrenheit, almost twice as hot as molten lava. This may be the most dangerous part of the flight. Mission Control is monitoring all the data from the spacecraft, and then we lose communication again. No data can penetrate the plasma. Orion is on its own. Orion is inside a fireball. Onboard systems ignite jets to keep the ship pointed correctly, so the specially constructed heat shield takes the full brunt of the inferno. This is the largest heat shield of its kind ever made. Orion's computers command the spacecraft to bank like an airplane, keeping a precise path to the landing site. Even though we've slowed from 20,000 miles per hour to about 300 miles per hour, we're still traveling amazingly fast. We must slow down to safely land in the ocean. Luckily, we have parachutes. Specially designed for Orion, the parachutes help us hit the brakes, but not too quickly. One day people will be aboard, so deceleration must happen in stages to keep things comfortable for the crew. The forward bay cover jettisons. Two drogue chutes deploy and slow the returning spacecraft down to 175 miles per hour. Then, the three main parachutes open. Once fully engaged, this canopy would cover an American football field. It takes parachutes this size and strength to slow our descent to 20 miles per hour, and then splashdown. For this first flight, we won't have astronauts inside, but we still have some very precious cargo. The flight data from this mission is stored inside the Orion spacecraft. While our flight might be over, there is still a lot of work to do. Onboard sensors recorded every detail, from launch to flying in space, to re-entry to landing. Flight tests are difficult and complex, but they give us confidence that the systems we have designed work under real flight conditions. It's great to be a part of this first space flight for Orion, and we're looking forward to beginning a new chapter in human space exploration.
Here's a look at some of the top NASA stories of 2014.
It's one small step for man, one giant leap for mankind.
With 2014 marking the 45th anniversary of Neil Armstrong's historic first step on the moon, NASA outlined plans for America's next giant leap in space exploration, to send astronauts to Mars. To prepare for that leap, NASA stepped up development in 2014 of many game-changing technologies and capabilities. The agency worked on solar electric propulsion technology, which could enable cost-effective trips to deep space destinations. Destinations that could include a human mission in the 2020s to an asteroid placed into orbit around the moon by a robotic spacecraft as part of NASA's Asteroid Redirect mission. NASA plans to announce more specific details in December about potential candidate asteroids and the design of the mission. The successful first flight test in June of the saucer-shaped low-density supersonic decelerator demonstrated an inflatable system that could be used to land heavier and larger payloads than ever before on planets with atmospheres. The International Space Station continued its role as a unique platform off the Earth where astronauts are working for the Earth with biomedical research and with payloads delivered by commercial partners SpaceX and Orbital Sciences Corporation, such as the first 3D printer in space, which could be used to manufacture parts in space. And the addition of an Earth science instrument to the space station's exterior to monitor ocean surface wind speed and direction for use in weather forecasting and for monitoring large-scale changes in Earth's climate. In September, NASA selected 2 U.S. commercial providers, Boeing and SpaceX, to develop the systems to transport astronauts from U.S. soil to and from the space station, with a goal of ending the nation's sole reliance on Russia in 2017. Development of the rocket and spacecraft designed to carry astronauts on NASA's journey to Mars progressed in 2014. The green light was given in August to start building the Space Launch System heavy lift rocket, following successful completion of a key review. New manufacturing facilities began testing operations, and prototypes built with new, more lightweight composite materials were evaluated. In November, the fully assembled Orion spacecraft was moved to its launch pad at Cape Canaveral Air Force Station in Florida for its maiden flight test in December. NASA's fleet of Mars robotic explorers continued its work in 2014. The Mars Atmosphere and Volatile Evolution spacecraft arrived at the Red Planet in September as the newest member of the fleet. MAVEN is on a mission to investigate how the past loss of atmospheric gases impacted the Martian climate through time. Samples from the first rock drilled at the base of Mount Sharp by the Curiosity rover provided the first confirmation of a mineral mapped from orbit by the Mars Reconnaissance Orbiter. And the science instruments were selected for the Mars 2020 rover, the next robotic explorer NASA will send to Mars in 2020. It will conduct unprecedented science and exploration technology investigations, including potential habitability of the current environment and directly searching for signs of past life.
NASA's role in studying and protecting our home planet has never been stronger.
NASA Administrator Charlie Bolden called 2014 the Year of Earth for NASA, with the agency planning to launch 5 Earth science missions within a year's time. The first images from the Global Precipitation Measurement Mission, launched in February, of an extratropical cyclone illustrated the mission's ability to provide next-generation detailed observations of global precipitation. In April, NASA celebrated Earth Day with a hugely popular online global selfie postings from around the world to help promote environmental awareness. And the test data from the orbiting Carbon Observatory 2 mission following its launch in July confirmed the health of the spacecraft's instruments. OCO2 will help track our impact on the amount of carbon dioxide in the atmosphere and the various human-made and natural sources of CO2. 2014 included new discoveries, new intriguing mysteries, and new reasons to explore our solar system and beyond. In November, the European Space Agency's Rosetta spacecraft, which has 3 NASA instruments on board, successfully landed its Philae robotic probe on the surface of a speeding comet, the first ever soft landing of a spacecraft on a comet. And NASA's Kepler Space Telescope discovered a new Earth-sized planet in April, about 500 light-years from us, that also may have liquid water. The agency's premier aeronautics research centers continue to work on solutions to help improve the safety, efficiency, and comfort of air travel while reminding people NASA is with you when you fly. A demonstration in November featured a wing that can change shape in flight. This could lead to technology for quieter and more fuel-efficient airliners. In September, NASA co-hosted an event that showcased 2 new technologies being evaluated that could improve takeoff time predictability of flights and help flight dispatchers choose more efficient routes around bad weather. And in May, NASA celebrated the renaming of its Dryden Flight Research Center to the Neil A. Armstrong Flight Research Center and designated Hugh Dryden's name to the center's aeronautical test range. That's a look back at some of the top NASA stories of 2014. Keep up with us in 2015 on social media and at www.nasa.gov/TWAN.
Preparing the Orion crew module for its first flight test in December actually began a few years ago. The crew module for Orion's flight test arrived at Kennedy Space Center in Florida in June 2012 and was transported to the Neil Armstrong Operations and Checkout Building High Bay for manufacturing, processing, and pre-flight testing. During the next 2 years, Orion prime contractor Lockheed Martin and NASA engineers and technicians built up the crew module from a green shell to a fully functional spacecraft. Many tests were performed to prepare Orion for its flight test. Orion's service module arrived at Kennedy Space Center and also was transported to the Operations and Checkout Building for build-up and processing. The module was completed with the installation of the fairings that protected in the early stages of launch ascent. Orion's heat shield, containing more than 200 instrumentation sensors, when installed. The heat shield will protect Orion during its re-entry into Earth's atmosphere and splashdown in the Pacific Ocean. Moving one step closer to the flight test, the Orion crew module was stacked atop the service module in June. Tile panels were installed around the spacecraft, and then both modules were put through their final system tests. On September 11th, the Orion stack was transported from the Operations and Checkout Building to the Payload Hazardous Servicing Facility. Inside this facility, the spacecraft was fueled with ammonia, hydrazine, and high-pressure helium ahead of its December flight test. The 4 major components for Orion's launch abort system, including the launch abort motor and the attitude control motor, arrived at Kennedy last year and were transported to the launch abort system facility for processing, testing, and integration. In late September, Orion was moved from the Payload Hazardous Servicing Facility to the Launch Abort System facility. Inside the high bay, the Launch Abort System was lowered and attached to Orion. The system is designed to protect astronauts if a problem arises during launch by pulling the spacecraft away from the falling rocket. Orion waited inside the Launch Abort System facility until the United Launch Alliance Delta IV Heavy rocket was ready for integration with the spacecraft. Earlier this year, the Delta IV core and starboard boosters arrived by barge in March and were offloaded and transported to the Horizontal Integration Facility near Space Launch Complex 37 at Cape Canaveral Air Force Station in Florida. The port booster and second stage followed in early May. The Delta IV central core booster was mated to the port and starboard boosters. Then the Delta IV second stage was mated to the rocket's central core booster. The Delta IV rocket for Orion's flight test rolled out of the Horizontal Integration Facility on September 30th and made the trek to the launch pad. In the early morning on October 1st, the nearly 180-foot-tall launch vehicle was carefully lifted into the vertical position and then raised into the mobile service tower on the pad. In early November, the Orion stack was transported to the launch pad and integrated to the rocket. Tests were performed to verify readiness for launch. After more than 2 years of work, Orion is now ready to soar on its first flight test.
Hi, I'm Michelle Nichols. Years ago, I told you about NASA's new idea for a spaceship called the Space Shuttle. It was an exciting time, and we showed what we can accomplish in low Earth orbit. During the shuttle era, we built the International Space Station. Astronauts orbit the Earth conducting scientific research in space for the benefit of all humankind. And now, there's Orion, NASA's newest space vehicle, rocketed off Earth by NASA's Space Launch System. The Orion spacecraft will be able to take us deeper into the solar system than we have ever gone before. So once again, we're about to begin a whole new era of exploration, with endless possibilities where we can boldly go. Discover more about NASA's new path into the final frontier right here at this website. Orion, I'm on board.
Upper stage LH2 secure at flight level.
35. 30.
Status check.
Go Delta.
Go Orion. Grain board.
25.
Flight lock in.
T-minus 20 seconds.
15.
Rofi ignition.
10.
The igniters have been lit.
9. 8. 7. 6.
5, 4, 3, 2, 1. And liftoff at dawn. The dawn of Orion and a new era of American space exploration.
Good engine control in the first stage. Passing 25 seconds. Velocity 1,341 feet per second. Passing 31 seconds, still looking good. Good engine control. Good chamber pressure in all three boosters in the full power mode. 40 seconds in. Standing by to go to the partial thrust mode in the core. And we have partial thrust command in the core. Core chamber pressure beginning to drop as expected as we're coming up on the 1 minute mark. Mark, 1 minute into the flight. still looking good. Good chamber pressure in the core booster in the partial thrust mode. Good chamber pressure in port and starboard in full power mode. One minute, 15 seconds into the flight. We have the hydrazine supply valve open in the second stage. 1 minute, 22 seconds in. Max Q, maximum dynamic pressure on the vehicle. Passing 124, Mach 1. Orion and Delta IV now transcending the speed of sound. 1 minute, 31 seconds in. Good engine control in the first stage. Coming up 1 minute, 40 seconds. Velocity now 1,341 feet per second. 1 minute, 50 seconds in. Still looking good. Coming up on 2 minutes. 2 minutes into the flight. Good engine control in the first stage. Port and starboard boosters still at good chamber pressures in the full power mode, and good core chamber pressure in the partial thrust mode at 2 minutes, 22 seconds in. Two minutes, 35 seconds in, still looking good. Coming up on the 2 minute, 43 second mark. 2 minutes, 43 seconds. The Delta IV of heavy Valkyrie now just weighs 1/2 as much as it did at launch, burning propellant at the rate of 4,744 pounds per second. Three minutes, 1 second into the flight. Still looking good. Passing Mach 5. Three minutes, 16 seconds in. Good engine control. Less than 1/2 minute remains on 3-booster flight. 3 minutes, 30 seconds in. We're standing by for the command to go to the partial thrust mode in the port and starboard booster. That command should occur about 10 seconds from now. And we've had partial thrust command. Port and starboard should be toggling down to the partial thrust mode. Standing by for main engine cutoff. We have cutoff in the port and starboard and separation. A good separation of the port and starboard boosters. Core booster now powering up to the full power mode. 4 minutes, 10 seconds into the flight. Good chamber pressure in the port. Correction, good chamber pressure in the core booster at 4 minutes, 18 seconds in. Four minutes, 25 seconds in, still looking good. Good engine control in the core. About 1 minute remaining on first stage flight. Four minutes, 46 seconds in, still looking good. Chamber pressure holding very well in a core booster as we're approaching the 5-minute mark. 5 minutes into the flight. Standing by to go to the partial thrust command. That partial thrust command about 15 seconds from now. Good engine control. Five minutes, 20 seconds in. And we have partial thrust command in the core. Core chamber pressure beginning to go down. As expected, standing by for MECO. We have MECO. The main engine has cut off. Standing by for stage separation. Each have stage separation. Heads is deploying. The nozzle has been extending. Standing by for igniter spark. And we have igniter spark, and we have ignition. Ignition on the second stage. Second stage chamber pressures beginning to rise.
This is Mission Control Houston. We're taking over commentary at this point as we come up on the first two critical Orion program milestones, the service module fairing panel jettison and the launch abort system jettison, standing by for those first two critical events. The service panel jettison has occurred. The three 13 by 14 foot panels have separated. And we have launch abort system jettison. The 361-pound solid propellant motor has pulled the launch abort system free from the upper stage and from Orion. Everything going extremely well. The first two critical milestones have been accomplished, and we are now processing telemetry from the Orion spacecraft through the tracking and data relay satellite system.
7, 6,
5, 4, 3, 2, 1. And liftoff at dawn. The dawn of Orion and a new era of American space exploration.
Good engine control in the first stage. Passing 25 seconds. Velocity 1,341 feet per second. Passing 31 seconds, still looking good. Good engine control. Good chamber pressure in all three boosters in the full power mode. 40 seconds in. Standing by to go to the partial thrust mode in the core.
We're 4 minutes away from the jettison of the forward bay cover at the very top of the spacecraft that will begin the chute deployment sequence. And we've reacquired signal from Orion, good data being processed. This view from the Icana unpiloted airborne vehicle over the Pacific Ocean, over the splashdown zone. Time to splashdown 7 minutes. Range to splashdown 127 miles. And now this view from Orion, its thrusters maintaining control. We're 2.5 minutes away from forward bay cover jettison. And this view again from the Icana aircraft over the splashdown zone. That view of Orion from the Icana. $25,000 feet. Time to splashdown less than 4 minutes. Forward bay cover has been deployed. Drogues have been deployed. Great video from the Icana. $15,000 feet until splashdown. Coming up on main chute deploy. From a waypoint over the Pacific Ocean, there is your new spacecraft, America. Drogues away. Main chute deploy. On mains, everything looking good. Good reefing reported. $4,000 feet. Three good main chutes reported from the USS Anchorage. That's confirmed here in Mission Control. From a high-speed rate of 20,000 miles an hour to a gentle return back to Earth more than 4 hours and 20 minutes after it took off on a Delta IV heavy rocket from the Cape Canaveral Air Force Station. $3,200 feet now until splashdown. $2,200 feet now. Winds at the surface just about 12 knots. Wave heights no more than about 4.5 feet or so. Perfect conditions for Orion's homecoming. This view from Orion itself of the chutes, helping it to descend gently towards its splashdown in the Pacific. 1,000 feet. We have splashdown. Splashdown confirmed at 10:29 a.m. Central Time. Orion is back on Earth. America has driven a golden spike as it crosses a bridge into the future. And we now have confirmation that Orion is stable 1, upright. Orion splashdown at a mission elapsed time of 4 hours and 24 minutes. But this day belonged to the team all the way around: Lockheed Martin, United Launch Alliance, NASA, all of the contractors involved in the development and testing of Orion for what turned out to be the most perfect flight you could ever imagine. Once again, you're looking at a variety of vessels and aircraft moving towards Orion in the initial phase of the recovery process that will result in Orion being winched and pulled into the flooded well deck of the USS Anchorage for its trip back to the port of San Diego, Naval Base San Diego. We now received a report that 3 of the 5 crew module uprighting system airbags at the top of the spacecraft did inflate fully. 1 was partially inflated. A 5th bag was not clearly visible to the initial recovery team members, but irrespective of that, Orion landed in an upright position under its 3 main parachutes in stable 1, as it is called. If you recall from the old Apollo days, stable 2 would have meant upside down. It landed stable 1. It splashed down in stable 1 and maintained its upright position through the use of its airbag system at the very top of the spacecraft. Recovery operations in the Pacific for Orion well underway. Just to recap, splashdown occurring at 10:29 a.m. Central Time. There's a good view of Orion. We wound up with 3.5 of the 5 crew module uprighting system airbags fully inflated. But nonetheless, Orion, under its main parachutes, which are being recovered by naval boats in the area, from the video from the Icana unpiloted airborne vehicle during the final moments of Orion's descent for its splashdown in the Pacific. They functioned perfectly, enabling Orion to touch down at a velocity of about 20 miles an hour or so for a very gentle splashdown in the Pacific. The coordinates, once again, where Orion is, you can see Orion right there. 23.6 degrees north latitude, 116.46 degrees west longitude.
40.
Upper stage LH2 secure at flight level.
35. 30.
Status check.
Go Delta.
Go Orion. Grain board.
25.
Flight lock-in.
T-minus 20 seconds.
15.
Rofi ignition.
10.
The igniters have been lit.
9. 8. 7. 6.
5, 4, 3, 2, 1. And liftoff at dawn. The dawn of Orion and a new era of American space exploration.
Good engine control in the first stage. Passing 25 seconds. Velocity 1,341 feet per second. Passing 31 seconds, still looking good. Good engine control. Good chamber pressure in all three boosters in the full power mode. 40 seconds in. Standing by to go to the partial thrust mode in the core. And we have partial thrust command in the core. Core chamber pressure beginning to drop as expected as we're coming up on the 1 minute mark. Mark, 1 minute into the flight. Still looking good. Good chamber pressure in the core booster in the partial thrust mode. Good chamber pressure in port and starboard in full power mode. One minute, 15 seconds into the flight. We have the hydrazine supply valve open in the second stage. 1 minute, 22 seconds in. Max Q, maximum dynamic pressure on the vehicle. Passing 124, Mach 1. Orion and Delta IV now transcending the speed of sound. 1 minute, 31 seconds in. Good engine control in the first stage. Coming up 1 minute, 40 seconds. Velocity now 1,341 feet per second. 1 minute, 50 seconds in. Still looking good. Coming up on 2 minutes. 2 minutes into the flight. Good engine control in the first stage. Port and starboard boosters still at good chamber pressures in the full power mode and good core chamber pressure in the partial thrust mode at 2 minutes, 22 seconds in. Two minutes, 35 seconds in, still looking good. Coming up on the 2 minute, 43 second mark. Mark, 2 minutes, 43 seconds. The Delta IV heavy Valkyrie now just weighs 1/2 as much as it did at launch, burning propellant at the rate of 4,744 pounds per second. Three minutes, 1 second into the flight. Still looking good. Passing Mach 5. Three minutes, 16 seconds in. Good engine control. Less than 1/2 minute remains on 3 booster flight. 3 minutes, 30 seconds in. We're standing by for the command to go to the partial thrust mode in the port and starboard booster. That command should occur about 10 seconds from now. And we've had partial thrust command. Port and starboard should be toggling down to the partial thrust mode. Standing by for main engine cutoff. We have cutoff in the port and starboard and separation. A good separation of the port and starboard boosters. Core booster now powering up to the full power mode. 4 minutes, 10 seconds into the flight. Good chamber pressure in the port. Correction, good chamber pressure in the core booster. at 4 minutes, 18 seconds in. Four minutes, 25 seconds in, still looking good. Good engine control in the core. About 1 minute remaining on first stage flight. Four minutes, 46 seconds in, still looking good. Chamber pressure holding very well in a core booster as we're approaching the 5 minute mark. 5 minutes into the flight. Standing by to go to the partial thrust command. That partial thrust command about 15 seconds from now. Good engine control. Five minutes, 20 seconds in. And we have partial thrust command in the core. Core chamber pressure beginning to go down. As expected, standing by for MECO. We have MECO. The main engine has cut off. Standing by for stage separation. Each have stage separation. Heads is deploying. The nozzle has been extending. Standing by for igniter spark. And we have igniter spark, and we have ignition. Ignition on the second stage. Second stage chamber pressures beginning to rise.
This is Mission Control Houston. We're taking over commentary at this point as we come up on the first two critical Orion program milestones, the service module fairing panel jettison and the launch abort system jettison, standing by for those first two critical events. The service panel jettison has occurred. The three 13 by 14 foot panels have separated. And we have launch abort system jettison. The 361-pound solid propellant motor has pulled the launch abort system free from the upper stage and from Orion. Everything going extremely well. The first two critical milestones have been accomplished, and we are now processing telemetry from the Orion spacecraft through the tracking and data relay satellite system.
7, 6,
5, 4, 3, 2, 1. And liftoff at dawn. The dawn of Orion and a new era of American space exploration.
Good engine control in the first stage. Passing 25 seconds. Velocity 1,341 feet per second. Passing 31 seconds, still looking good. Good engine control. Good chamber pressure in all three boosters in the full power mode. 40 seconds in. Standing by to go to the partial thrust mode in the core.